Hello to you from Chem Help ASAP. This video is a review of many electrophiles that students see during a two-semester sequence of Organic Chemistry 1 and Organic Chemistry 2. Because this video covers electrophiles, we'll also see some nucleophiles as well. The list of electrophiles covered in this video is not complete, but it should provide a somewhat thorough coverage. Your instructor may include additional reactions that are not discussed in this video. If I left out something obvious, let me know in the comments section. Finally, this video is meant to be a review and is recommended for students who have already learned some organic chemistry as opposed to beginners to the subject. An electrophile literally loves electrons. If an electrophile attracts electrons, then where does it put them? Electrons go into vacant orbitals. So electrophiles are characterized as electron pore centers with available vacant orbitals. What kind of vacant orbitals do we encounter in organic molecules? We see vacant p orbitals, such as with carbocations. We also have vacant pi star and sigma star orbitals. Admittedly, when we discuss reactions of electrophiles, we typically don't mention how electrons interact with the vacant orbital. We just say an atom or pi bond is attacked. Regardless, electrons from the nucleophile are interacting with a vacant orbital to initiate the chemical reaction. Okay, let's see some of these electrophiles in reactions. Carbocations are most often encountered with the SN1 reaction. You normally have some kind of leaving group leave. In this case, the leaving group will be a protonated alcohol that forms a carbocation. The carbocation is a fantastic electrophile. It is a vacant p orbital with a positive charge on carbon. Being so electrophilic, highly reactive, highly unstable, carbocations are actually not very easy to form. Tertiary carbocations are most stable, secondary carbocations are next. Less substituted carbocations are really tough to make. Carbocations react with weak nucleophiles. In this reaction, a chloride ion. The carbocation is a flat reaction center, so stereo control, attack from top or bottom face, is likely very poor. As always, anytime you have a carbocation, you need to be aware of potential carbocation rearrangements, whether a hydride or alkyl shift. Carbocations are also key intermediates in the Friedel-Crafts alkylation. An alkyl halide interacts with aluminum trichloride, a Lewis acid, and generates a carbocation intermediate, which can then be attacked by the pi system of an aromatic ring. I show a tertiary carbocation here. You could argue that some alkylations do not involve a true carbocation, but whatever the reactive intermediate is, it certainly behaves like a carbocation, including undergoing carbocation rearrangements. Another reaction that includes carbocations is the E1 reaction. In this reaction, the carbocation does not serve as an electrophile. Instead, the carbocation loses a beta hydrogen. It is deprotonated to form an alkene. This is not a nucleophile electrophile reaction. This is an acid-base reaction. Great, let's move to attacking pi bonds. Carbonyls. The CO pi bond are super common electrophiles. We can attack a neutral carbonyl, which is a rather weak electrophile, that requires a strong nucleophile, like this organometallic reagent. Sometimes carbonyls are protonated, which affords a much stronger electrophile. Protonated carbonyls, which are more reactive, can be attacked by much weaker nucleophiles, including water and alcohols. Note that calling a nucleophile or electrophile weak is not an insult. Reactions work best when one partner is strong and the other is weak. If you try to mix a strong nucleophile with a strong electrophile, you're likely to get an eruption in the reaction flask and a major mess in lab. Of course, if you try to mix a weak nucleophile with a weak electrophile, you'll likely not see any reaction. The Friedel-Crafts acylation also involves a CO pi bond as an electrophile. In the reaction, an acid chloride loses a chloride to become an acylium ion. Acylium ions are very strong electrophiles, strong enough to coax and attack by a weakly nucleophilic aromatic ring for an EAS reaction. That's it for the CO pi bonds. Let's see some CC pi bond electrophiles. Because the CC pi bond is not as polarized as the CO pi bond, there are fewer examples of CC pi bonds as electrophiles. One is the Michael addition, in which a nucleophile, often a highly stabilized carbanion, attacks the beta carbon of an alpha-beta unsaturated carbonyl compound. This carbonyl compound happens to be an alpha-beta unsaturated ester. The resulting anion can be protonated to give the nucleophile attached to what was formerly the beta carbon. You will sometimes see the nucleophile attack the carbonyl carbon instead of the beta carbon. Nucleophilic aromatic substitutions normally involve a CC pi bond in the aromatic ring being attacked. Aromatic rings are normally weak electrophiles and are only made sufficiently reactive if the ring has one or more strong electron withdrawing groups. These EWGs stabilize the anionic intermediate, the Meisenheimer complex, which ends up dropping a leaving group to get the substitution product. Again, the EWGs improve the electrophilicity of the aromatic ring. You can attack other pi bonds. On this slide, we show an aromatic ring attacking an NO pi bond. The active electrophile is a nitronium ion. This gives a ring nitration. The bottom reaction is a sulfonation. The active electrophile is protonated sulfur trioxide, and the ring attacks the SO pi bond. Note that these electrophiles are more reactive because they are both positively charged. Let's move to sigma bonds, specifically CX bonds. These are broken in SN2 reactions. The carbon of a CX bond is not obviously electron poor, and people tend to highlight the polarization of the bond to showcase the electrophilicity at carbon. Because the electrophile is weak, you need a strong nucleophile to perform an SN2 reaction, azide, cyanide, etc. If the carbon is a stereocenter, then you will get inversion. The leaving group does not need to be a halogen. Oxygen-based leaving groups like a tosylate are also common. Other sigma bonds can also be electrophiles and are subject to nucleophilic attack. In an electrophilic halogenation, Cl2 reacts with aluminum trichloride to form this aluminum complex. The aluminum with 4 chlorines is essentially an incredible leaving group, so the terminal chlorine is attacked and the Cl-Cl sigma bond breaks. This intermediate complex is a very strong electrophile. Here are some similar examples. In the halogenation of a ketone, you initially form an enol tautomer. The enol is nucleophilic enough to attack NBS, N-bromosuccinimide, which is typically protonated in the acidic reaction medium to make NBS more electrophilic. The reaction involves attack of the enol on the bromine and cleavage of the Br-N sigma bond. At the bottom of the slide is the dihalogenation of an alkene. Formally, Br2 serves as an electrophile, and attack by the alkene breaks the Br-Br sigma bond as the bromonium ion is formed. Not all reactions that break sigma bonds are nucleophile electrophile reactions. Here is a reaction of water with hydronium ion. The oxygen seemingly attacks the hydrogen to break the OH sigma bond. While that does happen, this reaction is a proton transfer. It is considered to be an acid-base reaction, not a nucleophile electrophile reaction. That was a quick review of common electrophiles in Organic 1 and Organic 2. Thank you for watching to the end. Please leave a comment, leave a like, or subscribe to the channel. Take care.